a whole new level of effort. I mean, it's definitely interesting. I give it that. Swift is really interesting, and the idea of being able to write code that directly accesses the, the C level speed is really interesting. I'm sure this idea is going to go places, but it hasn't really. It's not really ready for prime time yet. As you can see if you look at the Harebrained forum, there's a lot of people working really hard to get things working, and if you have the time to put that kind of effort in, that's great, but I don't think all of us do. So.
Yeah, I agree. So this is kind of unrelated, but if we're looking to kill time here a little bit, I've spent the last couple of weeks kind of like blitzing my way through the full stack deep learning little boot camp they had. And the company I work for, I'm the only data scientist. And so I've been trying to kind of figure out what our architecture looks like for training models and deploying stuff. I could answer questions or talk to that a little bit if there's interest.
I actually wanted to ask some things because that's something that I've been trying to think of, when I was focusing on this problem is the Fast.ai models, right? I was actually having a little bit of a problem, converting them to, as an API, a Flask API or, any other language. So has anyone tried that? Because I was having a lot of issues doing it, like how do you go about doing it?
Yeah, I could talk to that a little bit. So I think in general, like what you were saying there, putting it into an API is the right choice. And I think Flask is kind of the dominant one, although I've been playing a little bit with one called, I think it's called Fast.ai and one called Molten. And the kind of rationale behind that is that when you're serving predictions in production, you want to, not just make the predictions, but you want to write like to a log, kind of the inputs that are coming in, the time it took to do the inference, maybe the data distribution, stuff like that. And so having it in a framework like that makes that easier. And then as far as deployment, we basically landed on like 2 ways to do it. If it's like a small enough model, let's say, then we'll use a Aws Lambda, which is basically just like you can run arbitrary code and it handles all the scaling and where it runs and all that stuff. And if you can't do that because the model's too big or you don't meet the requirements for Lambda, then what we do is we package it up into a Docker container, and then we use like Kubernetes, which is like it orchestrates launching and scaling Docker containers. And so that's like the kind of overall framework is API to do the predictions and write logs and that kind of thing. And then either Lambda or Docker and Kubernetes. Does that help at all? Or do you mean I just realized, do you mean you're having issues with like exporting the model and like where you're running into trouble, I guess?
So actually, right at the basics, exporting the model and, just trying to use it as an API, like if I want to just use it as a prediction, if I pass it a single input, like if I made a model of the translation notebook, right? So if I say pass something in English and I want something in French returned, that was the issue I was having.
Yeah, and that actually totally makes sense that it's challenging because I feel like that is not a very well-defined part of the Fast.ai library, right? Because it's definitely geared towards research and kind of the cutting edge stuff. And I don't think a ton of things are getting put into production. And I've been playing around with that a little bit this week, where like, it seems like TensorFlow and PyTorch are sort of moving in the same direction from different points. So like PyTorch now has like JIT, which takes the dynamic computation graph and converts it into a static one. And that's important because it's like faster when you're doing inference. So I think that's the way to go as far as, let's say, saving a model is to use the JIT compiler from PyTorch and put it into a static computation graph. And then in your API, load up that graph, take the input that you get from like Flask, and then pass it through that. But the other tricky part is you have to handle all the like data pre-processing and all those things. So like one thing I have done is just use the like generic Fast.ai stuff, which is a little slow, where when the Flask server starts, it loads the model. And one of the tricks is you don't want to load the model every time you get a prediction request. You want to load it when the server starts, and then it stays there. And then when a prediction comes in, I think there's basically two ways you could do it. You could either apply your pre-processing, and then just say like model.predict, and then your input in the parentheses. Or if it's like a batch, you can load it in as a test set, and then say model.predict, data set is test, and that's faster for batches.
Right.
But why don't maybe I can kind of write something up and get some example code for next week and see if that helps.
Hey, Daniel,
Yeah.
I wonder if you could, since I have very little background in this full stack / data engineering side of things, and I think it would be useful, I don't know if other people are like that too, but it would be useful to me if you would explain what all of these technologies that you're referring to, Kubernetes, Docker, Flask, and I guess Jango is another one. What are the functions of all these pieces, and how do they work together?
Yeah, sure. You know what? Let me share my screen. I had something I was just showing my boss yesterday. Let me find it, and then I can kind of talk to a picture because I think that's a little easier. But yeah, it's all pretty simple stuff actually. It just it sounds complicated, which is like a lot of the stuff we do. All right, let's see. How do I share my screen? Is it possible?
I think there's a button in the middle of this.
Yeah, I see.
Oh.
Shame on me. All right, guys, let me know when you can see it.
We can see it.
Okay, good deal. So I'm pretty shamelessly stealing this or borrowing this from the full stack deep learning bootcamp thing, but they have like I think a good way of conceptualizing like the process of getting something from before you do the training to something in production. And I read somewhere, I think it was like McKinsey or Boston Consulting Group or something like that like 3/4 of machine learning and kind of analytics projects end up not getting into production or failing. And I totally believe that, from my experience in the corporate world, there's like a lot of people that can do this stuff. Well, there's not a lot, but there's enough people that can do the stuff we do, build a model, evaluate on a test set, but hasn't been a ton of like engineers or architect people that kind of understand all the pieces that go into it. And so tell me if this makes sense, but what I was thinking is I can give a really high level overview of like the 3 pieces and then maybe talk to the technology that we're going to use. Would that be a good way to go about doing it? It's a little off the cuff, so.
It sounds great. Yeah.
Okay, cool. So the way that these guys conceptualize it, which I really like, is they basically put into 3 buckets. They say there's like your data, there's the development you're doing, and then there's the actual deployment. And the data and the development, we'll go high level on, but basically they just talk through like, how do you keep track of your data? Like for me in the past, it's mostly looked like, I have 3 SQL scripts or something, and then I have a Python script that converts things and I run them manually, and I end up with like a JSON file or a CSV file or something. And then that's what I'm, training on. And so they suggest some maybe a little bit nicer ways to like label data or to keep track of it. That's probably worth going through. But the core idea there is that you'd want some automated pipeline to take your data from source systems and put it into training data so that you're not having to like manually scrub through it every time you want to, train a model. The development part, I think we're all pretty familiar with, which is once you have your data, you write code or you use code to build a model from it. They have a couple of resources they recommend, which are pretty cool. One of them was Weights and Biases, which is free for individual accounts. And it's you basically just add a callback and it writes data via like an API call to Weights and Biases. And it helps you keep track of like your accuracy over time, different metrics, that kind of thing. And so if you're trying like, 50 different hyperparameter settings or different models, it's a nice way to keep track of your experiments. But everything else, I think we're all pretty familiar with using. The deployment side I thought was the most interesting. And so basically the technology pieces I think that are important here are you have some code and data that you use to build a model, right? And so you want that data to be reproducible so that if you're training one model one week and then training another model the next week, it should be like the same data. Or you should have a process to build the same data set that you can compare models against. And so the first piece to that, I think, is that your code needs to be versioned, right? You need to be able to see the different, I guess, algorithms you've written or different code that builds a model. And you need to be able to relate that to your data. And so that's a pretty simple solution, is just commit your code to something like GitHub or GitLab or whatever. And as you try different models, make sure you commit it. But once you have a model trained, the kind of missing piece I feel like for a lot of us is how do we put that somewhere where somebody can use it, right, and make predictions. And so to me, the pieces that go into that are you have, whatever software libraries need to run, whatever dependencies you have. So that might look like, PyTorch 1.1 and Fast.ai 1.0.2 or something like that. Certain version of Pandas, certain version of NumPy, that kind of thing. Maybe you are doing inference on a GPU, and so you need to have a specific like CUDA kernel, something like that. And basically what you want is you want a way to package up all the software dependencies that you have. And that's basically what Docker does. It's like, it's similar to a virtual machine. It's not exactly one, but it's pretty close to that conceptually. And so Docker is really useful for, like, let's say I train a model and then I want to share it with Philip, but we have different versions of software libraries on our computers. And so something that runs for me maybe runs a little differently for him, or it fails because let's say PyTorch changes how one of their functions work, right? They say, okay, we don't actually take this parameter anymore. You have to call that separately. And so it breaks. The idea with Docker is that there's just an image that has like all the software libraries, everything that I need. And I can just say, run this Docker container or Docker image. And I don't have to worry about any of that stuff, like what to install, what versions, because it just does it automatically. And it's also really useful for putting things into production, not just because you like standardize the software libraries and what's running, but because let's say you have a website and you're serving predictions and we have like 10 people that use it. And then like there's a Reddit post that goes viral and now we have 100,000 people go to the website and we only have one container running. It's gonna break basically. It can't handle that volume. And so what you want is you want something that can scale out horizontally. So the idea is if we could just add, for the next hour while we're really popular on Reddit, if we could just add 100 more containers, there would be 100 different things to route those API calls to. And so that's where something like Kubernetes is useful. And what Kubernetes does is it manages the orchestration of Docker containers, basically. And so it lets you scale dynamically how much computational resources you need based on kind of the demand for your model. It's also useful for like web applications because you might have one Docker container that has your database in it and another Docker container that has your Flask API that's serving the predictions. And you might need to manage those, that kind of thing. But that's Docker and Kubernetes. Docker's the image where you have everything, all your code that's running, the software libraries, the CUDA kernels even. And then Kubernetes or something similar is what manages, the different containers.
I don't want to interrupt you. I will interrupt you, but I mean, and the reason is that I think you've just given the best high-level description of Docker and Kubernetes that I've ever heard in just about 2 minutes. So.
Oh, good deal. Well, it's pretty opinionated. So like, I'm sure there's plenty of people that would throw up if they heard my simplified explanation.
Anyway, move on. I'll go off.
All right, good deal. So that has been basically the way that things get put into production, I would say, for the last couple of years, for companies that are, more cutting edge. But there's this newish thing that Amazon and Google have started offering, which is basically just, hey, you know what? Don't even worry about this Docker container. Just tell me what code you want to run and I'll run it. And I'll manage the scaling and all that stuff. And that's like AWS Lambda, or I think Google has something called Google Cloud Run or something like that. And so the idea is you just have some piece of code that runs when you want it to. So I think I can actually show an example for something we built for work. And but basically, this is even simpler than Docker, and it gives you all the benefits of easily scaling and kind of managing stuff. So I built something really simple for work and it's not data science or deep learning or anything, but we integrate with a bunch of different source systems and they all have different data. And we have like a schema. So we deal with like resume data, and we want to take a resume and we want to convert it to a standard schema that we always use and then push it to a database. And so what I did is I wrote this Python code, and basically what it does is it loads in a JSON file, and then it runs some like transformation code. So for example, let's see if we can open this. It's pretty simple. It just has this like dictionary that it's trying to create, and it has these different functions that run to search through the source schema for a particular key. All right, so pretty basic Python. But the idea is that, let's say we have our partners give us 10 resume files from, in their schema. We want to have something automatically run and convert it into our schema. And we want it to work whether they do 10 million or 10,000 or 100 or whatever. And we want it to happen automatically. And we want there to be logs that kind of show what happened and all that stuff. And so the way Lambda works is you can set up triggers. So for me, a trigger is, we have these basically folders in S3 where they have access to load a file. And once a file gets created, it creates like an event in Amazon or AWS. And that object being created automatically triggers this function to run, this Lambda function. And then it hooks into like their automated logging and all that stuff. And so basically the idea is I didn't have to package up a Docker container. I don't have to worry about scaling. I just have some code that I want to run. And this could be based on triggers. It could be based on an API call. It could be based on anything. But once that event, that trigger happens, this code should run and produce some output. And in this case, we just write it to another S3 bucket. And that happens in the code. So this is super useful for, like, it gets rid of all the DevOps stuff. I just write the code to do what I want it to do. I say, give me the triggers for it, and then keep track of what happens so I can look at logs if something goes wrong. And so if you're serving a predictive model, this is a pretty sweet way to do it, is you could just take your Flask API, and I can dig into that in a second, but you take your Flask API, you put it into this Lambda code, which is just basically a zip folder that you upload. And then all you have to do is make the trigger an API call. API call gets made, it runs the code, creates the prediction, and then returns it. So Lambda is like the easiest way to, I would say, cost effectively deploy models and keep track of logs and all that stuff. But the limitation is it can only handle 3 gigabytes of memory, and the process has to run in 5 minutes. And I think I forget, there's something else. So it doesn't work for every model. Like some really large, huge model that's, you know, bigger than 3 gigabytes, or maybe you have like part of your pre-processing pipeline is to convert text to vectors. And so you're using like, you know, glove or BERT or something like that, and it won't fit in a Lambda function. Then you would package it up into a Docker container and use that to serve your predictions. So that's like high level how you would maybe put something into production. And let me stop there and see if there's any questions or thoughts, and then I'll talk about Flask or the API stuff a little bit.
So that one difference is that with Amazon Lambda, you build the application on their cloud machines, and that way all the dependencies are automatically taken care of, because and you're serving it off the cloud machines too. So that's why you don't. Whereas the Kubernetes and Docker's model works more if you develop something on your own machine and you want to share it with other people who have different machines. But this paradigm.
Let me make one correction in that you're still probably doing your development on a local machine regardless. And with Lambda, you still have to keep track of your dependencies. And this is one of the ways AWS makes Lambda work really well, is they kind of restrict, like the Lambda environment is basically pure Python. And to use a library like Fast.ai, you have to manage your dependencies a little differently. So that's maybe one of the trade-offs with Lambda, is that you still have to like manage dependencies, but the way you do it is you basically upload it to a folder, or as part of your script, you download the library into like a temporary folder. So you still have to deal with all that stuff. And so that's the disadvantage of Lambda, and that's why some people still prefer, and I kind of lean towards pure Docker.
But if you developed your code on Amazon, on AWS cloud, then, well, then I guess you'd still have to say, if you wanted to use Fast.ai, they'd probably still have to upload it there because they may not have it natively.
Yeah, exactly.
But I see. Okay. But all the other dependencies would be taken care of because it's already in their environment, in the Amazon environment.
Yeah, although I would say that I wouldn't recommend trying to use Lambda to like train a model, but I would recommend it to deploy a model that will serve predictions. Because it's meant to just, you know, execute whatever code kind of when a trigger comes in. So it wouldn't be great for training, but if you can package everything up, there's no DevOps. There's nothing to manage. It just runs, and that's the nice thing about it.
Daniel, I have one more question.
Yes, sir.
This is Mehul. So the great presentation. This is fantastic. So suppose I want to like run predictions with Fast.ai. So do I have to do like a git clone Fast.ai in my Lambda, or how would I get Fast.ai into my Lambda?
Yeah, great question. So basically there's two ways. One is, yeah, you could do like a git clone. And so the thing with Lambda functions, and this is kind of interesting, is they still have to start up, right? So it's doing kind of, it's not just magic, right? It's doing basically what a Docker instance is doing, in that they're just managing behind the scenes, all that stuff. So keep in mind that a machine has to be spun up, or a virtual machine or whatever, and then code will be executed. And so what'll happen is, once it gets spun up, if it needs to install libraries or that kind of thing, that will happen once, right? And then it's ready and it's waiting to receive predictions. But if another container or another Lambda instance needs to get spun up, it'll have to do that again for that new instance. And so, but yeah, you could either git clone, or you could kind of manage it yourself, and upload basically the software library folder into S3 and make it accessible via the Lambda function.
Okay, thanks. Yeah, I think this idea of this startup code is okay. I get it, because I used GCP before, and you know, when you start a GCP instance, you can put your startup code there too. Okay, thanks.
That's exactly it. Same exact thing. And I'm sure there's pros and cons to different approaches, and I'm still figuring out some of that stuff. But yeah, the key thing is, once your model's up, at least what I've seen, most industry applications, especially if it's like a web application or something, the inference time, or how fast it serves predictions, is super, super important, because I think we're all a little spoiled or used to really fast, you know, searches, really fast predictions, that kind of thing. And if you're waiting around on a website, then a lot of times you'll just leave. Okay, so that's like the high level of how you, like the frameworks that I've seen that make sense to deploy things. The actual like code or the mechanisms to deploy it, almost always, unless you're deploying to like directly to a cell phone, like a mobile device, almost always you'll do it as an API. It's just a good architecture design, and it sort of decouples whatever you're doing from the rest of the application. And then all the other developers need to do is call your API and have it return something quickly. There's definitely situations where you wouldn't do it that way. Like if you need ultra low latency, like super, super fast prediction time, like high frequency trading, for example, that's a good example. They probably wouldn't do it that way, because it would be slower than, you know, integrating it directly into the C code. I mean, that's where like something like Swift has maybe a lot of potential to be cool or useful. But 90% of the time, my experience, you'll serve it as an API. And so what that'll look like is, you know, the user or the application or whatever will make an API call to your model and say, here are the inputs, give me a prediction, basically. And that input could be a picture, it could be some text, it could be, you know, whatever. And so what you want is, you want a framework to kind of manage that stuff for you. So when you're writing code, hopefully all you need to do is say, here's an endpoint that a user might call. And then here's a defined behavior for what I do once I get that input. And so the API stuff is actually pretty simple, in that what you want to do is you want to load the model when your API server starts so that it's available. You want to receive the inputs, and you want to do some sort of test to say, is this valid input? So that maybe just looks like an assert statement. If it's not valid input, then you would return an error to whoever's calling the API. But assuming that it is valid input, you'd usually do some sort of pre-processing. And then you'd say like model.predict, you know, processed input, gives you the results. And then typically you just do two things. You say, you know, return those results. And you usually want to log kind of what happened to some sort of database or server or S3 bucket or something like that. And this is stuff that's easier to see if there's code. So I'll try to put something a little cleaner, a little better together. But that's kind of the high level of what I would say 2019 kind of putting models into production, the things you need to think through. Any questions, any thoughts?
Thanks, Daniel. That was really interesting. Also, I want to add that at the conference I recently was, there was another speaker talked specifically about what you just did about Docker and the advantages and disadvantages of Docker and Kubernetes and so on. So I think that's useful for all of us.
Nice. And Docker's kind of cool. Like, it's a little obnoxious to get going with, but once you understand it, you're like, oh, this is super easy. And it can be really useful if you, like, let's say that you have like 5 different models you want to try, and it's text data. And so it takes a long time to train the model, right? Because you don't know any of the Fast.ai transfer learning, let's say. And you want to just run it overnight. The cool thing about a Docker container is you could package up all your code and then just send those containers basically to run on like EC2 instances or something like that. And so it can be really nice also for collaboration, like packaging up everything and making it easy for different people to work in the same environment. And so it's one of those skills that even if you plan on always using Lambda, or you're going to have engineers to deploy stuff, it's not too bad once you learn it. And I think it's one of those skills that it's worth learning for data science.
I agree, yes.
Another question for you. Can you talk a little bit about how Jango and Flask fit into this framework?
Yeah, so Flask is probably, Flask and Jango, I would say, are the 2 most popular API frameworks in Python. And so they handle stuff like, how do you accept a request from a user and server response, and how do you handle, like when we go to a website and there's usually like there's some endpoint. So let's say our API was at, I don't know if there's a good example. Let's say it's just google.com/API/v1. You would want, if somebody sends a request to here, you might want that to be different than if they send a request to v2. And so you want some sort of code that manages the routing of how to direct like HTTP requests to what Python code will run. And there's a ton more that like Flask and Docker and Django do, but they're both frameworks to serve as like web server, micro kind of API things. And Django is more of like I would say a fully featured web development framework. Flask can do all that stuff, but it's a little lighter weight, which is why I think it's been really popular for deploying models. But yeah, both are designed to basically act as back-end web servers. I don't know, does that make sense?
Yeah, so I'm trying to understand how Flask and Django would work together with something like Kubernetes and Docker.
Gotcha. So I wouldn't, like Flask and Django, it's kind of an either or thing. But so let's say, like, here's a real simple Flask app. All it does is return hello world if you go to the endpoint. But what it is it's Python code that runs like a server application, right? And so the command you run is python app.py or whatever your app's called. And then what happens is if you go to whatever the IP address of the machine is, and you go to this place, so it's just like, let's say it's localhost, / then it'll run whatever this code is, and it will return that into your browser. And so where Docker comes into this is it's the environment that this code runs in. So instead of it running on your computer directly, or running on a server or a EC2 instance directly, the idea is you'd have a Docker container, which is kind of like a virtual machine, where that code runs. Does that make sense, or not so much?
Yeah, it does make sense.
Okay, good deal. And that's one of those things where probably the best way to get comfortable with it is just to like do this code basically and experiment with like change the endpoint and have the return do something a little different. And then, and there's great guides out there. And then you can start to do stuff like, how do I take input and all these things? And it's easy to go down that rabbit hole a little bit.
So does that full stack development course that you're talking about, does that go into all these details of how to build something using these?
It's pretty high level, and they kind of they basically assume that you have some software engineering experience, that you know how to do these frameworks. They go pretty heavily into the data and some of the different resources there. They talk a lot about testing and these things, but so I think it's a great resource to see what are the different components and how do I put them together, and gives you a lot of ideas for your specific use cases. But it won't do like a deep dive into the individual stuff. So like they'll have example code because they do a little lab of a Flask application. And they use Keras and TensorFlow in their example, but they build from start to finish an application that serves a model. But they kind of assume that you sort of know the basics of Flask and Docker and that kind of thing. Like they go over what it is, but it's not like a comprehensive overview. So I would maybe start there and then take the pieces that are interesting and then look at some of the beginner help guides for that stuff. And for Flask specifically, there's a great example from the guy that does the I think it's PyImage or Adrian something or other. It's one of the most popular ones. It's a computer vision website. He did I think it's called like a simple Keras app, simple Keras Flask API. Yeah, right here. This, and I'll post it in the Slack and resources. That's a fantastic little bit. I mean, it's not PyTorch or Fast.ai, but it's kind of all the components of how that basic API would look. And it's not a huge jump from this to doing it in Fast.ai.
That's great. Thank you.
Yeah, for sure. Probably can call it there. Looked at a couple things with data pipelines and data labeling. Yeah, and then the other thing that's kind of new for me a little bit, being coming from like a finance background, I'm super new to continuous integration and testing and that kind of thing, and so that was a really, I think, kind of useful thing for me to get out of the full stack deep learning stuff, is the different kinds of tests you might want to run and how to integrate them into your code base. And they have some great example code on their GitHub for that, and that's probably worth taking a look at. But that's pretty much it. Happy to field any questions or comments.
Just to I may mirror what you just said in order to make sure that I understood it correctly, or recapitulate in my own words what I think Docker is. So Docker is a framework that allows us to basically, it automatically installs all the packages, does all the whatever kind of system you need to run, and sort of automizes that. So and it does that in virtual containers, right? So it's a tool for virtualization, like in the past you may know VMware, where you have virtualization. You can call, for example, a Linux distribution from Windows and so on, and you can do that in a virtual way. And Docker is that, but just on steroids and way better.
That's exactly it. And the key difference of why it's better is that it's not a full like virtual machine. And so that's something that makes it lighter weight and faster, basically faster to start up and faster to run stuff a little bit.
That's pretty cool. Yeah.
Daniel, just one question I think was there in the messages was how much are you paying for Lambda? Because I have like some experience in AWS Lambda, and when I was using it, we were paid by the amount of requests we got. So how much exactly how are you paying for it?
That's a great question. And so I'm not paying anything, and I'm not sure what my employer is paying. But you're right, you pay like for the compute time. But it seems to be pretty cost effective, I think, given that like a Docker container, it's basically always on, at least, one of them, and you're always paying for that. And so in theory, depending on how AWS does their pricing, it should be less expensive to run Lambda because you're only paying for the compute time. But to be honest, I don't really know because luckily I don't have to pick up the bill for that. It's a good question though. That's starts to be real important when we're talking about like personal projects and stuff like that. It scales horizontally and it only costs me $10,000. Nobody wants that.
Yeah, because I've made a mistake of leaving my EC2 instances on for longer than I wanted to.
Oh, that's the worst feeling when you log in. You're like, what? It's still running? No.
I think that happened with Paperspace. Like when I first started with Fast.ai last year, Jeremy gave this discount, like Paperspace link. I set it up, and I clicked on stop, but it didn't stop. And 3 days later, I saw that I'd run a huge bill.
Oh man, I feel for you. I think we've all been there. All right, good deal. Well, I'm happy. Some of this stuff I probably can't share because it's like a little proprietary for our company. But once I've got it kind of finished internally for the direction I want to take things, then I'll see if I can package up something a little nicer into a blog post or something and share it. And I definitely encourage you guys to check out the full stack deep learning because all this stuff is my opinionated take on their opinionated take. It might be better to go directly to the source for a lot of it.
Thanks,
Daniel.
That
I have a
really,
question about.
yeah.
I have a question about the full stack deep learning. They were mentioning kind of exam they gave at the end, and they were saying like how like that's like a 45 questions that will kind of help you understand all of deep learning. Did you see it anywhere?
No, I didn't. I know exactly what you're talking about. Or the last few slides are showing some examples. I don't know if they're open sourcing that or making that available. But if I see something, I'll share it out in the Slack.
Thanks.
So Daniel, that was a really great off the cuff presentation. I think this thing is being recorded, even though nobody, even though we're not in a class. But I mean, I think your presentation was so nice that somebody could actually tune in and listen to it and get a lot out of it. So I really appreciate that. I wonder though if you could tell me if this class, if we're talking about a deep learning full stack class bootcamp, is that free? Is it offered on Coursera? Where is it offered?
Yeah, it's totally free. Basically what they did is they had people pay when they did it back in March. And then they put all the lectures on YouTube and all their labs with solutions on GitHub. So why don't I just point you guys to
Yeah,
that?
if you could post that link on the chat, that would be terrific.
Definitely, yeah, I'll do it right now. And and it's very digestible. And one of the kind of cool things too was Jeremy Howard did a lecture, like a guest lecture as part of it. Here it is. All right, I'll post the GitHub and the YouTube videos.
Great, thank you.
I just shared I found a link from their website. It's not the YouTube, yeah, but let's put a YouTube one too. I was just downloading their PDF slides. Thanks for sharing. This is great.
Yeah, super happy to. Thanks for listening. Gave me honestly great practice for when I have to convince our architect on some of this stuff. So thanks for being guinea pigs.
Yeah, one
Glad to do
different one way we are doing, so we use deep learning in production, and one difference is, so we don't have we don't need it like right away, so we are doing like segmentation of images. So we've been a little bit old school. We're still like, we are using Conda environments. So we have like a Fast.ai Conda environment, Keras Conda environment, and then before we do training wherever on AWS and then copy the weights. So that's been a problem, right? We copy our weights into a GitHub repository or somewhere. We had to tag it, and then in our Conda environment, when we run our script, we say, okay, we activate the Conda environment and then run the inference. So it's interesting to see this, like Docker and other ways to do it.
Yeah, and this stuff I feel like is evolving not quite as fast as like deep learning libraries and techniques and stuff, but it's, for me 2 years ago, the way we were deploying stuff into production was in SQL Server, in Microsoft's thing, because they were starting to let you run Python there, and so it changes pretty quick, it seems like. And I bet within the next year there will be something like Lambda, but you just upload a Docker container. That would be the perfect solution, in my opinion. All right, Philip, bring us home.
Sorry, I didn't understand that.
I was just joking. That was my stupid way of saying I'm done.
Okay, I see. Yeah.
Yeah, so if there's anyone that has a mini presentation, I don't know if anyone has anything they want to present. Now would be the time. We actually got through, it's already 10:10, so it's just about that time when we would switch to mini presentations. So if anybody has one, speak up, and if not, we can either continue the discussion or close the meeting. Okay.
So I was actually planning to do something on the attention mechanism, which was like an extension from Sanyam had presented on sequence to sequence networks. I didn't manage to get a PowerPoint presentation or anything, but I can explain it on the conceptual side of it. So if that's fine, then I can go ahead with that.
That would be awesome, man.
Yeah, go.
Yes. Yeah. Just give me 1 minute.
Well, while you're getting that set up, I posted this, I think, in the Slack a while ago, but I wanted to float it out there in case anybody has any brilliant ideas. So one of the problems I've got at work is I have a collection of job postings, which is, we have like 150 million job postings, and I'm trying to extract from each job posting some skills. So like a data scientist, maybe, it pulls out Python, TensorFlow, PyTorch, something like that. I've seen some stuff like singular value decomposition and that kind of thing, but does anybody have ideas on how to go about doing that don't involve labeling a ton of data?
Just off the top of my head, I think there is, at least I've read, there is an approach where you can let the data be automatically labeled via a supervised or semi-supervised learning approach. But I'm definitely not that just light it up in my head. But I can't tell you anything more deeper in that. But I think there might be a way. If I understood you correct, you're looking for a way to kind of automate the whole labeling process, because you might be pissed they make you do it, and there's definitely a way.
Yeah, basically something. I mean, I don't mind labeling some data. Of course, I feel like when you get to that large volume with so many different jobs, you would have to label a very large number of skills, unless there's some sort of transfer learning or semi-supervisor. Anyway, so if people have ideas or cool papers or something, feel free to ping me, and I would would definitely.
Or outsourcing to Mechanical Turk or something like that.
Yeah, that's a good idea.
So
Okay,
Daniel,
so
you correct? Oh, I'm sorry. Is the mini presentation ready?
yeah, actually I won't be able to actually, the code won't be, I don't think anyone would probably make sense of it on screen share. So you can go ahead with the question. I was thinking of maybe explaining it, and if I can find a good diagram, I'll show it.
Okay, I don't want to get in your way though. I mean, if you're ready to start, I'll just not ask my questions.
Yeah, you can go ahead with the question. I'll just get the diagram ready.
Okay, great. So Daniel, if I understand, you have 150 million job postings, and you're trying to pull out the main features to describe these postings, or is that what you're saying?
Yeah. So it's like the keywords or skills that like the most important things or most unique things or something along the lines of that.
Oh, well, you could start by, this is just simple, but you could start by doing some kind of a word cloud thing and seeing like which skills pop out, which are the most likely skills to be mentioned in these postings, and then just hand make a list of them, just take the top 100 or something like that and then go with those. I don't know.
Yeah, that's probably what I'll end up needing to do. I'm kind of like the bureaucrat now that's like, but machine learning can do it for me.
Machine learning is still going to find the most likely, words. And there was a question from Jess, and she said, what are you trying to achieve by doing this? What's the business goal?
Yeah, so basically, the idea here is like what we're trying to build is a model that takes a job posting and maybe some user input, like specific skills they're looking for, and then takes a list of, let's say, 30 resumes and ranks them from best to worst in terms of like let's say has the most qualifications for the job. And so we don't have like much labeled data for this. And so my idea is to basically extract like a query from the job posting that I can make against Elasticsearch. And then I can use the ranking from Elasticsearch as like a weak signal, and then start to put in some like adversarial sampling and try to build a better model from that weak signal. This is something like that.
And I don't know much about NLP, but I know that there are, and some folks that are on this call might know more, but I know that NLP does things like looks at documents and pulls out the most important ideas or words or something in those documents. And that's a general procedure that a lot of people use in NLP, and I think you could just apply that. I don't know what it's called though, but you could just find an implementation of that and apply it to your.
I think it's called summarization.
Yes, that's the word I'm looking for. Yes.
Yeah, that makes sense. And I bet there's probably some pre-trained models that would make it a lot easier or reduce the amount of labeling I would need to do. So let me play with that and I'll report back to y'all.
That's an exciting database, 150 million.
Well, exciting until you got to work with it, and then it's frustrating.
Yeah.
All right, so I'll just start.
Okay.
Is my screen visible?
Yes, sir.
Yes.
Yes,
Okay.
it's visible.
So just for like a revision, this is how a normal sequence to sequence network is. Just to go back, sequence to sequence networks are really good for machine translation. And the reason why they're pretty good is because, each word in like a sentence is, it's kind of, it's related. So, like the word embeddings, if you take this pretty simple sentence. You know, it's pretty related. So an LSTM or a GRU, it processes them together, and then it makes a context vector, which is denoted by this blue arrow over here. And then it passes it on to the decoder for one of the inputs, along with the start token over here, which will be the first input. And then this would be giving an output, which would serve as the hidden state as well as the input state for the next network, for the next cell, and so on. So this was a conventional sequence to sequence network. Usually in a sequence to sequence network, what happens is the context vector that is chosen is just the hidden state of the last LSTM or a GRU cell, and the previous cells aren't really used. And that's actually what they found out was in the paper as well. If you go with the attention paper, was it didn't make a lot of sense. I'm paraphrasing Jeremy here from last year's lesson, that it didn't make a lot of sense throwing away the hidden states of the previous words as well, because certain words play a bigger role for certain sentences over here. So like this is a local Indian language. So this is, if you go by this sentence, good is the fourth letter of a fourth word over here in the English sentence, but this is the literal translation for good over here, which is the second word. So they found out that context, just having a single context vector from the last hidden state of the LSTM encoder cell wasn't the most appropriate solution. So they wanted a way in which you could take all of the hidden cells from the LSTM and then pass it to, you know, to the decoder in some way. So that's how the attention mechanism came away. So I'll just go with the diagram over here. So if you can see this diagram over here, this is actually a pretty good diagram that explains the attention mechanism in some way. This is the first step. So you pass the sentence through an LSTM encoder or a GRU encoder. Each step gives one hidden state. These hidden states are then concatenated together. And then that, along with the last hidden state, which is taken separately, is passed through a feed forward network, and which is then you calculate the softmax, because you want to calculate the probability ratio in some way, you know, like which word has the probability of being most effective for the first state, like for the first word in the decoder, if that's clear. So you get these, you get this over here, E1, E2, E3, E4, E5. And then you can calculate the context vector that way. 1 second. Yeah, is the diagram, like, are you able to see the diagram?
Adjust your flowchart, right?
Yeah,
Yep.
sorry, the flowchart, yeah. Yep. So this is basically how the new context vector is calculated with respect to an attention vector. And that, along with the first word of the decoder, which is usually the start or anything like this, is passed through the decoder GRU. And that is then repeated for the other words over here. So if you look at over here, you get a hidden state D1, which is also the output when you pass the context vector with the first word. And if you look down for the second step, D1 and the hidden states are then passed through a feed forward network. The similar thing, you get the scores, you calculate the softmax of the scores, then you compute the context vector, and then you concatenate the context vector from the output from the previous step, and then it goes ahead this way. So that's actually the attention mechanism in pretty similar simple steps. So any questions on that?
I have question. I don't totally get it, but I don't know what my question is. So
Yeah, actually rushed through it, so that might be possible. So maybe if you ask the question, I can go back and make it more clear.
no, I thought your presentation was good. If I don't understand, it's because of me, not you. But maybe, so the way I kind of understand it is you have like some hidden state from your input and you want to decode that. And what the attention mechanism helps you do is like you're multiplying the vector by another vector basically of equal length, I think. And it changes that hidden state based on what it's paying attention to. Is that like the kind of right?
Yeah, you can say attention is like a weighted vector, you know. So the main goal of attention is to give weight to certain parts. And basically what happens is like the encoder part, right? So if you have like 5 words in the encoder and there are 5 LSTM cells. So each cell, if it's passed through, like, you know, I am giving this presentation. So I will, you know, give a word embedding for I, we pass it through an LSTM cell, you get an hidden state. And then I am, and then am is then passed through along with the previous hidden state, and then this is calculated. So the encoder was just calculating the hidden states of each of the words in the initial sentence. But what we were doing is we were only passing the last hidden state to the decoder. And what they decided in this case was, let's pass all of the hidden states to the decoder, but let's not pass it all together. We'll, you know, just find out, let's say, a percentage score, you know. So, and when you want to find out the probability score, like if this is 0.2 probability, so they went with a linear network with a softmax, you know, just to calculate which of the hidden contexts have, you get certain scores, and then you multiply each of the scores. You'll get around, if you have 5 hidden states in the encoder, you'll get 5 probabilities, and each of those 5 probabilities are then multiplied with the hidden states of the encoder. So you get some attention score, and then that is concatenated along with the word in the decoder for computing.
Okay, I think that totally makes sense. It's like you're making a classification on the inputs and you're saying, give me like the percentage I should pay attention to each of them. And then you're using that to, let's say, you know, bias it towards some of the inputs and against others. And then you take that, concatenate it together, and that's what goes into the decoder.
Right.
That totally makes sense. That's a great explanation.
So I understand the softmax and the probabilities, but so I understand that you're passing, let me just recapitulate what I think you said. You're calculating these hidden states, and then you're multiplying, you're also calculating these softmax probabilities, which say how important each hidden state is. Yeah. And then you're multiplying the probability times the hidden state.
Yeah.
And then those, let's say there's 5 hidden states. So then you've got 5 hidden states, which each corresponds to a number. You've got 5 softmax probabilities that each correspond to a number. You're multiplying those 2 vectors together, element by element. And then you're passing the resulting 5 numbers into the decoder. So, so what I don't quite get is, what does the hidden state represent? What does that number mean?
I think one of the tricks, or sorry, go ahead.
No, you can go ahead, actually.
I was gonna say, one of the tricks is that you're concatenating it together. So you remember the stuff about like contextualized vectors, like the problem with word2vec, and I think there's a real similarity between hidden state and vector representation, is that one word has the same representation regardless of the context.
Right. Right, right.
And so the contextualized embedding kind of solves that by looking at the words around it. And attention, I think, sort of does the same thing with the hidden state, because it's saying like, look, it's not just the hidden state of this one word, it's some combination of the hidden states of all the words around it. But I need a way to say, how do I combine these together? And so what the attention mechanism learns is basically how to combine the things together, how to squish them all into one hidden state and pass that into the decoder.
But I thought that each hidden state corresponds to one of the words in the sequence.
Yeah, that's my understanding.
Yeah,
So,
each hidden state corresponds to one word, or maybe a combination of hidden states may correspond to one of the words, because there's no like guarantee that a 5-word encoder in a machine translation problem would give you a 5-word decoder, you know, in another language.
I see. So, but what? So why? So why do you need the probabilities? Why isn't it sufficient to just pass in the hidden states to the decoder?
I think because you want to weight them, right? So you wouldn't want to pass in all the hidden states equally weighted for every step of the decoding process. You would want to discount some if the hidden state isn't relevant to decoding at that step.
Okay.
So like if you just added them all together, you'd have one vector. But if you multiplied 4 by 0.01, they would only make a very minor change, right? And that's the idea, I think, is how do you put those hidden states together in a way that, let's say, pays attention to the right inputs or kind of words.
Right, but you're not combining all the hidden states into one. You actually are maintaining 5. Let's say we have 5 words. We have 5 separate numbers. So you know, so let's say the hidden states were all the same. Let's say they were all 1 or something. And then you calculate the softmax probabilities and then you weighted them. So I guess I can see that where after you weight them with the softmax probabilities, it says, okay, no, this word was more important. You know, like let's say one of the softmax probabilities is the highest, and then that may be the middle word. And so then it would tell you, well, oh, the middle word is the most important word in this sequence of words. I guess that.
I think the trick, my understanding is, it's not that you're like let's say that the representation was a single number for each hidden state. It's not that you're making a new array that is like hidden state 1, comma hidden state 2, comma hidden state 3. You'd be making one new number, basically. So you'd be passing in like a 3.2 or something like that. But the hidden states are vectors. And so I think what they mean, and I could be totally wrong, but I thought like well, maybe it is a concat, like across that. Maybe it is.
It's a concat. They concat all the hidden states, and each of the hidden state is then, you know, I think you can call it an element-wise multiplication with the probability.
Yeah, that's what I understood.
Okay.
Yeah.
But I guess it's kind of like channels in like an RGB image or something. It's not maybe extending the array. It's adding on dimensionality to it, and then that's how it uses it.
Yeah, I can call it like that. But I guess, you know, each word embedding is like if you multiply something with one single word embedding, would be like, say, most word embeddings are 300 in length, so like 1,300 vector. So you get something like that. So it'd probably be a 5,300 or something like that vector, and that would then be passed through a linear layer along with.
Okay, that makes sense. That makes sense. So it's like you might just have some of those dimensions be like 0 or pretty close to it if it's not attention to them.
Yeah.
Okay, that makes sense.
So any more questions on this?
Yeah, there was a question from the chat, which was asking how the attention mechanism is different from the transformer architecture.
So the transformer architecture is on my to-do list for reading, but from what the brief understanding I have is the attention mechanism is the basis of the transformer architecture. It's just that they've done away with the sequence to sequence, they've done away with I think in the initial LSTM part. I'm just reading it, and you can see the diagram for the transformer architecture on Google. It doesn't have the LSTM part for the sequence to sequence. I think they have one linear layer, and I think there is something they call a multi-head attention, which then it's passed through that directly. So they've done away with the LSTM part because I think they felt that when you have when you have a sequence of words which are like the assignment I was doing, the work which I was doing was summarizing newspaper articles, and the newspaper articles were sometimes 1,000 characters long, 1,000 sentence words long, and the headline was just 8 to 10 words. So in those cases they found out that maybe the transformer architecture does better than a normal seek to seek. So that's something that I have to read, but yeah, the attention is definitely the basis for the transformer architecture, and it does away with the seek to seek part of it, but attention is definitely a part of it.
So does attention help you to recognize the most important words in the sequence? I mean, say you have, like you say, a newspaper article.
Yeah.
When you apply this to it, does it identify, are you actually summarizing the newspaper article in a small number of words? Is that what you're saying?
Theoretically, yes. That's what the papers, and I think that's what the BERT architecture that Google released, that's also something that specializes in one of the things. So I would say theoretically, yes. I still have to test it out, but yeah, that's the goal of attention.
I see. So this actually could be applied to Daniel's problem of reading in job descriptions and pulling out the most important pieces.
Yeah, it could. I'm just not sure about in an unsupervised way, but yeah, definitely it could. In a way, if they have some baseline resumes, then definitely.
Did you actually put the paper that you're summarizing up on the chat, or can you?
Sorry, I didn't get you.
The paper that you're summarizing, could you put it on the chat at some time later, maybe?
Oh, I wasn't doing this paper that was summarizing. Actually, I was doing this data set, this New York Times. So I can share my Google Drive link that has the the CSV file if anyone wants to have a go at it.
Yeah, and any if you have a write-up on it, that would also be useful to share.
Yeah, I'll definitely share a write-up in the coming week. Actually, I was trying to get that seek to seek working, and it wasn't working. So I tried at the last minute to do Fast.ai's translation notebook, which Jeremy had done last year with attention. But I think the main problem with that was my encoder had a huge, the sentence length was huge, and the decoder was just 8 to 10 words, and my encoder was like 1,000 words long because the newspaper article was huge, and it didn't work very well.
I see. All right.
But it did manage to get like some words, like if there was an article about China, then the headline would have China in it.
Okay, thanks.
Yeah, this was a great presentation, man. I feel like I'm starting to understand attention, and just give me a bunch of ideas. So thanks for sharing. I feel like some stuff's starting to click.
Yeah, sure.
I have one question, Abby. So when you when you use attention, how long of a sequence can you use? Like you were saying, 8 to 10 words. Is that as much as it can handle, or can you handle 30 words or 40 words or 100 words?
So this is something that I have to completely see, because usually from whatever notebooks that I've come across on GitHub, and even the data set that Jeremy used last year for translation, the sentences were pretty close in length. You know, he did an English to French translation. So the English sentence would be 10 words and the French sentence would be somewhere close.
I see. So that's the current limitation is something like a dozen words or something. It looks like. I mean,
I think with with the sequence to sequence architecture, maybe that's a issue. And I think with transformer and maybe something like a BERT, or maybe even a ULM fit, I don't know, it might be better.
I see.
Yeah, I know. I didn't understand it, but I read the paper talking about universal transformers, and basically what they, I don't totally get it, but what they said, the goal was that when they had large documents or a large training set, using like a sequential model like an LSTM, the computation time was prohibitively expensive, let's say. And so the idea behind the transformer, I think, is that it doesn't require sequential input. So it lets you train longer sequences and more data faster, or parallelize stuff, something like that.
Yeah, because I think in a sequential model, if one of the sequences is not that big, then you'd be passing a lot of unknown tags. The ones with Jeremy was saying, XX, UNK, those kind of tags, and that's usually what then ends up coming out in that.
Well, okay, we're at roughly 10:40. We could end now, and then we'll have to figure out what to do next week because there's no more lectures to summarize.
Yeah, so there's a thread started about some ideas what to do next. I can dig it out and put it again on the Slack, and maybe we can put some ideas there and maybe meet next week at the same time and same group. And
yeah, and definitely let's do that. And definitely, if somebody has a mini presentation that they want to do, that would be great. Maybe even more than one.
Yeah,
so.
there was an idea to just basically restart from lesson 1 of part 2 to kind of get better idea of what it is.
Yeah, that's true.
Maybe we can figure out that before the meetup, so we can
yes.
someone can prepare. So if anyone's got any ideas, I'll dig out that thread and put it again on the Slack, and maybe we can decide what we want to do.
Okay, sounds good, Michael.
Yeah, fantastic.
Okay, thanks everybody. Let's end the meeting right now. See you next week.
See you guys next week.
Okay.
See you next week. Bye.
Bye.